Hello everybody, it's nice to see some of them here, very nice. And officially today is first lecture of the course with different name, single variable calculus, but I would prefer to consider all those versions of calculus as one very long course. Moreover, introduction into calculus was supposed to consist of 30 lectures, and because of my family circumstances, there were given only 29 lectures. So, in fact, today, by the prepared material, this is better to consider as the last lecture of Introduction to Calculus. So, I'll numerate as as 30, right? So, and section 30.1, inflection points. And I'll start with the definition. If f is continuous in, let's say, x naught minus delta, x naught plus delta, convex upward in x naught minus delta x naught, and convex downward in x naught plus delta, or convex downward in x naught minus delta x naught, and convex upward in x naught plus delta, then x naught is called a point of inflection. Of f of x. So, roughly speaking, it means that the function changes the direction of convexity. Oops. Okay. Could I start from the beginning? Okay, I may read what is written in principle, but is it clear? I guess it's clear. Everything is written, and yeah, so just inflection points, everything is written, just definition. I said nothing else, at least nothing essential. And now, once again, roughly speaking, what means inflection point? It means the direction of convexity of a function changes when we pass through that point. But that is not precise. And let me give an example. Okay, firstly, a trivial example, just example 1. Consider f of x equals to x cubed. So, you see, if we take second derivative, it is written to, okay, first derivative of the first derivative, so 3x squared prime or 6x. And we see that second derivative is positive for x positive, and it is negative for x negative. It means the graph looks like, okay, like this, right? That is y equals to x cubed. So you see, here we may take as a delta arbitrary positive number, and x naught is 0, of course, right? X naught is 0. So 0 is a point of inflection. Why? Because the function is convex upward for negative x and convex downward for positive x. Now, that is rather trivial example. And now more complicated example which shows that those words function changes the direction of convexity, that is not precise. So example 2, I will modify slightly. Let's say f of x equals to x cubed times 2 plus sine 1 over x. I don't want to compute second derivative. It is a rather huge expression. Why? Because we can understand what happens easily by the picture. So we know how it looks like 2 plus sine 1 over x. Sine 1 over x, it oscillates, right, between -1 and 1, and oscillations are denser, more dense, when we approach to the origin, right, to x equals to 0. So oscillations will be more dense when x approaches to 0. So sine 1 over x oscillates between -1 and 1, hence our multiplier oscillates between 1 and 3, right? So I may draw two curves. One curve is precisely copy of our former example, y equals to x cubed. Another is y equals to 3x cubed. So that is y equals to 3x cubed. And our function, okay, here it is not good, of course, like that, right? And our function oscillates between them somehow, right? So it oscillates, and oscillations are denser when we approach to 0. And a symmetric picture we can find from the left-hand side, right? And now, you see, here it is convex up, downward, right? Next interval, convex upward, downward, upward, downward. And those intervals will interlace more and more often, right? When we approach to 0. But we are not able to find any delta such that there is an interval 0 delta, right? So if you take arbitrary small delta greater than 0, then what happens inside this interval? Our function oscillates infinitely many times, and the direction of convexity also oscillates, right? It means we cannot find an interval where our function is convex in one side, let's say in 0 delta, and in opposite side in minus delta 0, right? So it means 0 is not an inflection point, right? But remember what I said before about inflection point, roughly speaking. Roughly speaking, direction of convexity changes when we pass the point. It changes, right? It changes infinitely many times when we approach to that point, right? So that means that those words, just to say the function changes direction of convexity, they are not precise. So that is why the definition is precise. So here everything is precise, right? And when we change a little bit, I mean those roughly speaking changes sign of direction, changes direction of convexity, it becomes wrong. Okay. That is what's about inflection point. Now, the main section for today, 30.2, how it is called, constructing the graph of a function. Constructing the graph of a function. So that is, let's say, a top of the chapter about applications of derivative. So now we should collect together the knowledge about the first derivative, the second derivative, and so on. And also there is one thing which is necessary here as well. So let me start again with the definition. The line y equals to kx plus b is called an oblique asymptote for y equals to f of x as x tends to infinity or minus infinity if the limit is x tends to plus infinity or x tends to minus infinity. F of x minus kx plus b is 0. So oblique asymptote means what it means by definition. We draw a line y equals kx plus b when it is asymptote for a function. When our function approaches somehow, in fact, it can approach like that. It is also an approach. Y equals to f of x, right? That is also an approach. So if it oscillates, but oscillation will be smaller and smaller, it is also an approach. The main point is that limit is 0. That is limit as x tends to infinity, right? Plus infinity. The function may have two oblique asymptotes. One as x tends to plus infinity, another as x tends to minus infinity, right? Also, if k equals to 0, then the asymptote, the oblique asymptote, will be horizontal, right? That is a particular case. And how to compute, how to find an oblique asymptote of a function? Okay, we can find easily from that equation, right? So, first of all, if we have an oblique asymptote, then what we can do? So we know the limit is 0. Then, look, what follows? The limit, such limit, okay, I'll consider only the case x tends to plus infinity. X tends to minus infinity is quite analogous. What can we say about this limit? What is the value? Look, this tends to 0, right? 1 over x tends to, as x tends to infinity, to 0. 0 times 0 is 0, right? Yeah. Then, look, let me rewrite. So we have limit as x tends to infinity, f of x over x minus k minus b over x equals to 0, right? And we know this tends to 0, right? So what follows? It follows that the limit as x tends to infinity, f of x over x equals to k, right? And it gives us the rule how to find an oblique asymptote. So, how to find an oblique asymptote? We compute firstly k equals to limit as x tends to infinity or x tends to minus infinity f of x over x, right? That's first step. If such a limit, finite limit, exists, right, then the next step is what? If we find k, then look at the definition. K we found, right? There exists such a k, right? So we can deduce that second step, b equals to the limit as x tends to infinity or x tends to minus infinity of f of x minus kx. That's it, right? So these are two steps to find an oblique asymptote.
Excuse me.
So the last direction of convexity when we are the last direction of convexity. Can you say me what is the last direction of convexity when we approach to 0? It's impossible. There is no last direction of convexity, right? So that is it. Once again, that's a good idea to say that the last direction of convexity. But once again, what means the last direction of convexity, right? In principle, it's possible to give such a definition, but then we need to define what means the last direction of convexity, right? That is...
Excuse me. Sorry.
What is it?
Can you hear me?
What is it?
I have a question.
Oh, sorry. That is not a good idea to disturb me by a voice. If you have a question, please write it down. If you are not satisfied by my answer, then it's another story. Then you can say it by voice, because otherwise it may be absolutely crazy. Okay, but I wonder if I answered the question about why did you convert the limit? Why did you convert the limit f of x minus kx plus b? Why we convert? I'm not sure if I understood correctly the question. Yeah, now I understand. So the question why we that is not convert. I didn't convert that limit into one. That is an implication, right? So it doesn't follow from this equality that one, right? But from this equality it follows that one, right? So why I did it? Just to compute k and b. That's all. So the only reason was to find how to find k and b. Yeah, that is in definition, and that is it explains why we are interested in asymptotes, because yeah, so they determine how the function looks like when we approach to infinity. And by the way, we can also observe another thing, namely, so what happens if the limit if the limit of a function is infinite. So what happens if the limit of a function as x tends to finite a, let's say, minus 0, is infinity, plus infinity or minus infinity, doesn't matter, right? So, okay, let plus minus, and here minus infinity as well, right? Doesn't matter. Plus or minus. What happens? Look, let me draw a picture. So, okay, let a be here, that is y. So a plus 0 is plus infinity. X equals to a. So when x approaches to a from the right hand side, f approaches to plus infinity, so it looks like that, right? Okay, I will not draw further, right? So once again, this is also a case of similar, right? So the graph approaches to the line, but now this is the vertical line, right? So it means that if this happens, then x equals to a is a vertical asymptote for f of x. So, and you see that in fact to be a vertical asymptote, it is sufficient to suppose that the limit is infinite just from one side. It may happen that from other side, let's say like that, graph is like that. Even if the function has a graph like that, right, still we can say x equals to a is a vertical asymptote. So from one side, the graph approaches to the asymptote, and it's enough. We don't care about other side. Okay. Now the algorithm. Okay, it is not so obligatory to write down everything just in the same direction of as it is given in the lecture notes. So I will not try to fulfill everything. So let me erase now, and now the algorithm. So the algorithm for studying the function, for studying the function y equals to f of x and plotting its graph. Of course, you can say, now we have a lot of computers and so on. This is not a problem to plot a graph, right? You are right, of course. But you see, I remember once I tried to use some online plotter to check a graph of a function with parametric function, better to say not a function, curve given parametrically, and I was very surprised when the graph was completely different, and I understood that one piece of graph was lost because of different scales. So different parts of graph had very different scales, and of course it was not a very good plotter, right? But nevertheless, a piece of graph was lost completely by the computer. So sometimes it happens. Of course, in very few examples, and definitely not in the examples like given in your lecture notes and like you will be asked for in written exam. I hope it will be in spring session. Okay, so first step, determine the domain of y equals to f of x. Maybe the range, but that is not quite often is possible easily, because the range, it's another story. Sometimes you can do it, but in very few cases, in fact. Okay. Next point, which is quite logical, continuity. Continuity of f of x and behavior at boundary points of the domain. Including, we can do it just now, including asymptotes, because boundary point of the domain, okay, if infinite point is a boundary point, then oblique asymptotes just describe the behavior at infinity, right? And same is about vertical asymptote, right? That is behavior at a boundary point. A is a boundary point of the domain. Or when you consider continuity for a function like that, right? A is included into domain, right? But the function is not continuous, right? So it means that when we consider continuity, definitely we'll need to determine also vertical asymptotes. That is why I include asymptotes here. Okay, third, some particular cases should be determined also. Some evenness, right? Oddness of a function. Periodicity. That is also can be done. Yeah, you see, maybe it can be done before. It doesn't matter. Okay, fourth, intersection points with coordinate axis and sign of the function. again, sign of the function, if possible, because there are examples when you cannot determine the sign of the function for sure. I mean, like if you have a cubic polynomial or a polynomial of large degree, then to determine the sign of that polynomial you need to find roots, and that is maybe a big problem, right? So if you can do it, please do it, of course, right? So after that, plot a sketch of the graph. That is not again, that is not an obligatory thing, but quite often it happens to avoid mistakes, because you see, after that what you do? Compute the derivative. Of course, if you can do it, right? Because it may happen that there are points where derivative doesn't exist. Determine intervals of monotonicity and extremum points. Seven, compute the second derivative. Or maybe I should indicate y prime, y double prime. Determine intervals of convexity and inflection points. And the last step, plot the graph. So why I recommend to plot a sketch? Because sometimes you can do mistakes in calculations of derivative, and definitely they cannot contradict main details of the sketch. So let me consider an example. It seems now we should get a break, and before break maybe a few words also about this evenness and oddness and periodicity. Why it is included here, and once again maybe it can be done before. Because if the function is even or odd, then you need to draw the graph only for positive facts, right? After that, you can use symmetry of the graph. Same is about periodicity. If the function is periodic, then you need to draw the graph only on a period, and then just to expand the graph by periodicity. Okay. let's have a break. Okay, we continue. Yeah, good question. Fifth step. Yeah, it's correct. Fifth step is a less accurate version of our graph. That's all, right? What we can draw here, nothing else. In fact, there are examples when it's practically impossible to realize seventh step, for example, right? So the second derivative contains polynomials of higher degrees, and you have no possibility to find precisely roots. So it may happen. Okay, so example which is given in your lecture notes: f of x is x cubed over x squared minus 2. So I'll follow my version of the algorithm because, once again, it is not obligatory, but asymptotes, evenness, oddness, periodicity, intersection points, those things should be done, right? Yeah, those things and those things should be done in any case. And this sketch, okay, it's once again, same question. If we make a mistake in derivation, the graph wouldn't change to another, or it just makes contradiction. That is just what I said. So if you change graph after finding the derivative, it means, if you change it completely, right, it means that you made a mistake in computations. Okay, so let's start with the domain, right? What is the domain of our function? Here it's obvious, that is minus infinity minus square root of 2, minus square root of 2 square root of 2, and square root of 2 infinity, right? Because the only point which should be excluded are roots of that equation, right? Maybe the range, poof, we cannot, right, determine the range. So, second step, continuity. Okay, obviously the function is continuous everywhere on its domain, right? Because if x not equals to plus minus square root of 2, then we can use theorems about continuity. So as a ratio of two continuous functions and with denominator, non-zero denominator, we obtain the continuity. So behavior at boundary points. Okay, if we compute the limits, x tends to, let's say, minus square root of 2 minus 0 f of x. Okay, yeah, you see that here it is more convenient firstly to compute to study third step, but okay, it doesn't matter. let's do here. So if x less than square root of minus square root of 2, then x squared minus 2 is positive, right? And x cubed is negative, so we have minus infinity. Also, we may compute other limits. X tends to minus square root of 2 plus 0 f of x. Here, x squared minus 2 will be negative, so we have plus infinity. And it means that x equals to minus square root of 2 is a vertical asymptote. Analogously, limit as x tends to square root of 2 minus 0 f of x. Here x squared minus 2 is negative, so it's minus infinity. Limit x tends to square root of 2 plus 0 f of x is plus infinity. Hence, x equals to square root of 2 is a vertical asymptote as well. Now, limit as x tends to plus or minus infinity, doesn't matter, f of x over x, that is limit x tends to infinity x squared over x squared minus 2. We can compute by dividing to the highest degree, 1 over 1 minus 2 over x squared. So 1 over x tends to 0, and we obtain 1. Then the limit as x tends to infinity f of x minus kx is equal to the limit x tends to infinity x cubed minus x times x squared minus 2 over x squared minus 2, and we can compute, that is limit as x tends to infinity 2x over x squared minus 2, largest power is second, so 2 over x over 1 minus 2 over x squared, and we obtain 0. So it means that y equals to x is an oblique asymptote as x tends to infinity, and in fact same computations are valid for x tends to minus infinity as well, right? Because nothing changes. So we completed second step, the behavior at boundary points of the domain. Boundary points are infinities and plus minus square root of 2. Now we can observe that f of minus x is minus x cubed over x squared minus 2, that is minus f of x, so f of x is odd, and it means that we can construct only the graph for positive x. And fourth step, intersection points with coordinate axis. So f of x equals to 0 is equivalent to x equals to 0, obviously, right? And it means that we have the only intersection point 0, 0. And we can determine also sign of the function, and taking into account third step, I don't care about negative axis, so it means I look only onto two intervals, 0 square root of 2 together with square root of 2 plus infinity, and the sign is plus here minus here. That is f of x, right? F of x. And the sign of f of x. Okay. Now it means we can proceed with first step, plot the sketch of the graph. So, what can we do here? Look, what we know at the moment. We know one point of the graph, 0, 0. We know the vertical asymptote, x equals to square root of 2. We know the oblique asymptote, y equals to x, y equals to x. So it means that the graph should approximate the line y equals to x as x tends to plus infinity, right? And also we know that when x tends to square root of 2 plus 0, f of x tends to plus infinity. So when x approaches the square root of 2 from the right hand side, f of x approaches plus infinity, right? So after that, okay, we know somehow it should be there. Okay, I can draw like that, but of course it may happen that it will be like that. I don't know at the moment, right? Both sketches are possible here, right? I cannot choose between them at the moment. Both do not contradict the information up to now, right? So that is why I am talking about sketch. You see, there is a very big freedom. And also, okay, what we know, as x tends to square root of 2 minus 0, f of x tends to minus infinity, and somehow it comes to 0, right? And the graph should be symmetric because of oddness, right? So it means I should draw also minus square root of 2 vertical asymptote, so the graph should be symmetric. So I don't know what happens, either that or something like that. I cannot choose between those two versions. Maybe even worse, right? Because definitely I have no idea about the behavior somewhere here, nothing. But the sketch, I mean the behavior as x tends to infinity, as x tends plus minus square root of 2 is clear, more or less, right? So concerning the behavior as x tends to infinity, there is a freedom, but not so large, right? From one or other side. Okay, now we can proceed with derivatives. So I will erase asymptotes. Okay. So now y equals to f of x, right? I want to draw the graph of a function y equals to f of x. So sixth step, y prime. So by the rules, derivative of numerator times denominator minus numerator times derivative of denominator over square of denominator. We compute 3x squared. I can only do the sign for positive x. Yeah, of course, there was a question. Let's explain the last line one again. Last line about oblique asymptote. I don't know. And there is a question. Computations of. Do I need to explain once again? It seems I need to explain once again the computation for oblique asymptote. Do I really need? Okay. No, I think everything was written in so many details. I mean, just okay, maybe at the very end I will return to computation of asymptotes if there will be time. So, and another question, why we can only determine the sign for positive x? Yes, that is because if it is odd, yeah. Definitely, yeah. We just use oddness. And we can extend our function to the negative axis by oddness. Okay. Minus x cubed times 2x over x squared minus 2 squared. That is 3x power 4 minus 6x squared minus 2x power 4 x squared minus 2 squared. That's it. X squared times x squared minus 6, right? X squared minus 2 squared, right? I have computations here. Let me check. 9. Oh my god, I changed slightly. Okay, so it means I consider slightly different example. Doesn't matter. So then we have this. So look, what we should determine now? Intervals of monotonicity. It means we solve the equation y prime equals to 0, and it gives x equals to 0, x equals to plus minus square root of 6, right? So once again, we don't need to consider negative axis. So square root of 2 square root of 6 should be enough. And look at the derivative then, y prime. So the sign for derivative, look here, we start from plus and we change sign when x passes through square root of 6 minus. Don't change sign when it passes square root of 2, say minus. Okay, we can draw also for minuses, but not necessarily, but it is easy here, right? So don't change for 0, and we change, don't change it minus square root of 2, and once again change minus square root of 6. So direction of monotonicity is like that, right? Okay, maybe that one as well. And you see that here we have minimum, and also we need to find the extremum points completely. It means y f of square root of 6 we need to compute, and it gives us what it gives, square root of 6 cube over 6 minus 2, and it gives 6 square root of 6 over 4, or 3 square root of 6 over 2. And so it means we have square root of 6, 3 square root of 6 over 2 maximum point, and symmetrically minus square root of 6 minus 3 square root of 6 over 2, sorry, minimum point here, minimum point, minimum, and here maximum point. Okay, sixth step is completed, right? So seventh step, second derivative. So seventh step, y double prime, we compute the derivative of the first derivative, x squared minus 6 x squared minus 2 squared prime over x squared minus 2 power 4. It gives 2x times x squared minus 6 plus x squared times 2x minus 2x, x squared times 2x times x squared minus 2 squared minus x squared times x squared minus 6 times 2 times x squared minus 2 times 2x over x squared minus 6 power 4. Now we observe that we can cancel x squared minus 2, and after that we can take 2 outside as a common multiplier, right? And then what we have? Okay, 2 outside. X cubed times x squared, x power 5, minus 6x minus 6x cubed plus x cubed plus x5, x power 5, then minus x cubed times 2x cubed plus 12x and minus 2x cubed. 2x cubed. Here, okay, 2 is common multiplier, so x cubed minus 2x power 5, 2x power 5, and plus 12x cubed. That's it. Over x squared minus 2 cubed. And that is, so what we have here, 2x5 is cancelled. What's about x cubed? 12 minus 10. So 2x cubed. 2x cubed. Sorry, common multiplier 2, I forget. 2 times 2x cubed plus 12x, right? 12x over x squared minus 2 cubed. That is 4x times x squared plus 6 over x squared minus 2 cubed. That is the second derivative, and we can draw a picture. Once again, I don't need to draw it to the left of 0, but okay, that is not so difficult, so we can do it. Minus square root of 2, and you see what's about y double prime. It changes sign at every of those points, so like that, and it means directions downward, upward, downward, upward. So now we can plot the graph. So you see that I can erase this version of the graph because direction of convexity is positive here. Also, I can draw more precisely the graph near the origin, because you see now we know the derivative at 0 is 0, right? So it means that x equals to 0 is inflection point. Inflection point. Should be indicated. And this inflection point also has horizontal tangent. That is about this part of graph, and also that is square root of 6 and 3 square root of 6 over 2. That is minimum point, and analogously symmetrically is here minus square root of 6, so minus 3 square root of 6 over 2 symmetrically here. That's it. So you see that the sketch of the graph was practically very similar to the final result, right? Okay, so sorry, I didn't want to change your example, but it was occasionally. And it seems, yeah, practically the graph is almost the same up to some numerical values of the maximum and minimum, right? Nothing else. Okay, that's it. And of course I have only 10 minutes, but I wanted to give you some impression about no problem. Maybe, do I need to compute? Oh, maybe it's a good idea, yeah, because the time is almost over. So maybe let's compute oblique asymptote also by L'Hopital rule. Why not? We can do it quicker. So once again, to compute oblique asymptote, let me recall, we need to compute those limits, right? And we can proceed also using L'Hopital rule. So x squared over x squared minus 2 and infinity over infinity. Hence, we can differentiate both numerator and denominator. It gives that one and 1, right? So we can use also L'Hopital rule as well. And b, which is limit as x tends to infinity f of x minus kx, that is limit as x tends to infinity. Okay, let me give, maybe I made it very quickly, minus x. So we take common denominator x squared minus 2 over x squared minus 2. That's it. Limit as x tends to infinity to x over x squared minus 2. Once again, we have infinity over infinity, so we use L'Hopital rule, what gives 2 over 2x, and now we obtain once again 0, right? And maybe I computed here x limit as x tends to plus infinity, right? For minus infinity, no difference. When there is a difference, that is, for example, of course, I'm not going to give everything, I mean, to plot the graph, but just to compute an oblique asymptote. So, example 2, f of x equals to square root of x squared plus 1, let's say, right? So, look, What's about oblique asymptote? Limit, okay, k equals to limit as x tends to infinity, square root x squared plus 1 over x, right? So, x tends to plus infinity. It means that I can use the equality x equals to square root of x squared, because x tends to plus infinity, it means x is positive, right? So then we obtain square root of and divide by largest degree, and it gives 1, right? After that, b equals to limit as x tends to infinity, f of x minus kx, that is limit as x tends to infinity, square root of x squared plus 1 minus x. And how we can compute it? Multiply by algebraic conjugate, that is sum of those expressions. It gives x squared plus 1 minus x squared, square root x squared plus 1 plus x. Okay, and after that we obtain limit as x tends to infinity, 1 over, okay, let it be like it was, right? And you see both terms tend to plus infinity, right? Hence the denominator tends to plus infinity as well, so it's 0, right? So it means y equals to x is an oblique asymptote as x tends to plus infinity. What happens for x tends to minus infinity? Of course, we can refer to symmetry. Look, the function is even, right? If its graph, look, what we know. We know the graph approaches to y equals to x, right? As x tends to plus infinity. Because of evenness, what will be about oblique asymptote as x tends to minus infinity? It cannot be y equals to x, right? It should be symmetric. Hence, what is oblique asymptote? Y equals to what? Minus x, right? What is symmetric? Minus x. Symmetric, right? Minus x. But of course, this can be done also analytically. How? Oops. As x tends to minus infinity, what will be different? Look. Minus appears here, right? Because if x tends to minus infinity, then minus should be placed here. After that, here we have minus 1. So plus, change, and obtain y equals to minus x is an oblique asymptote as x tends to minus infinity. Okay? Okay, that's all for today. Thank you.